Talk about a little bit more on the system where you have a feedback control. Yeah. The given formula. So today we will see that if you have given a feedback system, with that feedback is the system stable or is it unstable? And that's very important because that's the whole purpose of doing all this mathematics, that you should know if the system is stable or not stable. So we'll talk about the stability, but this is something I just forgot last time to write, that procedure to obtain TS for a block diagram is called Mason's formula. Mason's given formula. It's just a hint. So let's assume that you have a block diagram which is given to you like this, and this is GS, and then you have a feedback here, HS, which is here is negative, positive, you have RS, and you have output CS. So in that case, according to the tables I sent you, what will be here? I sent you a document in which there are dozens of diagrams. Right? Very useful document. So what will be here? It will be
GS over 1 plus
G over?
G over 1 plus
Yeah,
G.
G over, very good, 1 plus HG. Now, the transfer function will be equal to output over input. We already know that. Now, of course, then your Laplace inverse, if you want to take the Laplace inverse here, then CS will be equal to TSRS, which is very simple, and if you take inverse Laplace of CS, will be equal to inverse Laplace of, TS and RS. Now this will be your CT, right? So this you can solve the above equation to get CT, which is basically your response function. Now, this is something very basic. It's nothing really. So where are my papers? Are they moving? Oh, good. Yeah, keep moving them. Yeah. So these are the basic definitions which we covered last time, and then we solve for CT, which is the basically response function. Now for a mass spring dashpot system, or mass spring dashpot system, we already know that you will have basically this equation which we derived And I'm sure that you already now know this equation. Kx is equal to ft. And if we take Laplace on both sides, you will say it will be Fs. And if you take Laplace, you will get ms squared plus Cs plus k multiplied by capital X is equal to Fs. And this is also below. So from here, the transfer function is basically your xs over your fs. And in case we simply use, ds is xs over, so this will be then, if you put xx from here, then fs and fs will be cancelled, and you will get ms squared plus cs plus k. Now, the equation on the denominator is called the characteristic equation. So your equation, so let the denominator be equal to 0. So let ms squared plus cs plus k equal to 0. Let this equation make equal to 0. This is called characteristic equation. This is called characteristic equation. And the roots of this equation will decide the general nature of the system performance. Very important comment. Roots of this equation will decide or will determine the performance of the system. The nature of performance will be known from here. So which is mostly we are looking at the stability. Stability. So let me repeat. Very simple things. Here we have really a very simple system. We find this is something Mason's general formula, and we did very complicated thing last time, and there was a mistake because I put it wrongly. This over 1 plus GH, actually it should be G over 1 plus HG because it's the